The topic of my paper is the impact of sea current on underwater transportation using 4 autonomous underwater vehicles. First, I will tell about the different types of unmanned underwater vehicles. There are two main types of unmanned underwater vehicles which are generally used. The first one is autonomous underwater vehicle, which is torpedo shape, is untethered, is fast in speed. It can cover a large area in less time, and it is pre-programmed, so autonomous. Uh, it is used in a lot of operations by the military and industrial fields, uh, such as the search and rescue operations, the survey operations, as well as the inspections, underwater inspections. The the only disadvantage of autonomous underwater vehicles is that they can only move precisely in one direction because they are under actuated. They have one or two propellers in maximum. So if they have to move to a certain location, so they have to turn. Um, on the other end, remotely operated vehicle, they are tethered, they are slow in speed, uh, they can only cover a small area because of the limitation of the cable. But the greatest, the major advantage of a remotely operated vehicle is that they have a special maneuvering capability that is called zero steady turning radius. That is, they can move in any direction with precision without turning. So if they have to go in the X, Y, or Z direction, they no need to turn. They are over actuated, more thrusters than the degrees of freedom, and this is very beneficial for the precise operations. So in my case, as I'm working on the underwater transportation, uh, I will recommend this vehicle as and I used it in my research. Uh, but the disadvantage of it is that it is tethered. So if we can use the remotely operated vehicle and use it autonomously, we can get the advantages of the remotely operated vehicle, which is very important for the payload stability, as it will avoid large relative motions between the vehicles during the transportation, which will ensure the stability of the payload. So that vehicle I call in my research as hovering autonomous underwater vehicles. There are some vehicles available which are of box shape and are used autonomously, but here in this research, I'm using the Minerva HAUV, which is still the remotely operated vehicle. But if in future that it is used autonomously, it could be a great advantage, especially for the multi-vehicular transportation. The main modes of transportation are land and aerial vehicles. The underwater transportation is not usually used because of the high hull resistance, which is obviously due to the higher density and viscosity of water. So it's not efficient in terms of the fuel consumption, but it is advantageous in certain circumstances and in certain fields, such as in the military field, where the military payload has to be transported undetected. It can also be advantageous in the other sectors, such as the offshore platforms, where the underwater structures or rigs are required to be transported and installed in underwater positions with precision. However, the underwater transportation is only recommended for the short range operations, and the recommended procedure is to take the payload to near as possible to the exact location, and from there the underwater vehicles take it and transport it to the destination. The So the question arises, why multi vehicles? Uh, Other than using giant vehicles, it is very difficult to carry large or heavy payloads by a single vehicle. And the giant vehicles also have limitations because they have a payload deck which has a certain size and shape. So if there is a random payload, it cannot be transported, it cannot be carried. So, but with multiple vehicles, the heavier as well as the random payloads could be transported, and we can increase or decrease the number of vehicles based on the requirement. If there is a heavier payload, we can increase the numbers, and if the payload is smaller or lighter in weight, we can decrease the number of vehicles. So it is cost effective as well, as we are using the number of vehicles as per requirement. The other advantage is that the multi vehicles, when they are used cooperatively, they have the fault tolerance, that if one or more vehicles in the system are damaged, the mission or the task can still be continued with success. There are two methods of multi-vehicle transportation based on the connection. So the first method is the rigid body connection, in which the vehicles are connected to the payload through solid links. This is easy, a simple model, especially for the simulation model. It is easier to analyze because the whole system is assumed a single rigid body, and a centralized control system is enough to control the system. On the other hand, flexible connection method, where the vehicles are connected to the payload through flexible links, it provides some independency to the vehicles in their motions. So there are the vehicles independently move to keep their position, orientation, and the swing angle with respect to the payload. The decentralized control system is recommended for such system, as each vehicle is independently controlled to keep its position with respect to the payload while maintaining the stability of the payload. In my paper, in this paper, I've used the rigid body connection method, where the Minerva AUVs are connected with the payload rigid connection. So so single rigid body was developed, and a centralized control system was implemented. Uh, as I said that I used Minerva ROVs, and I use them autonomously. So I call them Minerva HAUVs. In this system, in the system for this paper, I used four of Minerva HAUVs. Each Minerva HAUV contains one transverse thruster, two axial thruster, which are installed at an angle of 10 degrees, so that it can provide both the motion in surge and sway, and two vertical thrusters. So the total transverse thrusters will be 4, 8 axial thruster, and 8 vertical thrusters for the 4 vehicles of the system. These 4 vehicles are connected to a cubic payload through cylindrical links. The why Minerva ROV or the modified form is used is because this vehicle is operated by NTNU, Norwegian University of Science and Technology, and they have done a lot of research on it, and a lot of research papers are available on it. So the data is readily available. As I said earlier, I said yesterday in my previous presentation that I've kept the nonlinearities and coupling in the development of dynamic model in order to keep the simulation model as close as possible to the actual system. So I developed the nonlinear coupled dynamic model using the Newton-Euler formulation and vectorial mechanics. The two reference frames were used, that is the earth fixed frame and the body fixed frame. The position and orientation of the system were defined in the earth fixed frame, whereas the velocity, forces, and movements were defined in the body fixed frame. The dynamic model consists of the kinematics and kinetics. The kinematics describe the motion of the system without including the forces and movements, which are then taken up by the kinetics. The kinematics gives the change of the position and orientation of the system, and that is equated to the relative velocity in this case, which is the difference between the actual velocity and the secant velocity, and which is multiplied by the transformation matrix, so that we get the change of position and orientation in the earth fixed frame. Whereas the kinetics takes into account all the forces, such as the inertial forces, Coriolis forces, damping forces, and the hydrostatic forces, which are equated to the thrust forces and moments. The mass matrix, capital M, is equal to the rigid body mass and the added mass matrices. And the Coriolis forces are the summation of the rigid body Coriolis and the added mass Coriolis forces. So VR is used because we are in this paper I looked into the sea current effect, so which will affect the overall velocity of the system, and the velocity which will be looked into is the relative velocity, that is the difference between the actual and the sea current velocity. The assumptions which were taken are shown as rigid body of constant mass, that is the whole so the whole system is a rigid body, and the mass distribution on the system doesn't change during the motion. The whole system is assumed deeply submerged, so no wave effects. The interaction effects with the other bodies and the seabed are ignored, as well as the sea currents are applied, which are constant and irrotational. As I told you earlier, that the propulsion model for this system would have 4 transverse thrusters, 8 axial thrusters, which are installed at 10 degrees with the horizontal. So it will have the components in both x and y direction, and 8 vertical thrusters. Each thruster can apply between 300 Newton and 340 Newton. The 300 Newton is the operating value, and 340 is the maximum value, which was tested for the Minerva HAUV at NTNU. The interesting thing about this model is that the axial thrusters on HAUV 1 and 2, they would apply in the x direction, and 3 and 4 are applied in the transverse direction. So in total, the axial thrusters have an angle of 10 degrees, but overall all the axial thrusters on the 4 vehicles would have equal effect in surge and sway. The thrust allocation matrix was developed, keeping the effect of all the thrusters about the center of the combined body, that is the center of the payload. The parameters were calculated. For the Minerva HAUV, the hydrodynamic parameters were taken from the research at NTNU, whereas they were calculated for the cylindrical payload and cylindrical manipulator and the payload. The effect of all the parameters, the effect of all the hydrodynamic parameters were taken about a combined center, which is the center of the payload. The hydrostatic parameters, again for the Minerva HAUV, are available, whereas the manipulator was selected such that it's neutrally bound. For the payload, the volume was kept at 1 meter cube, and then the payload weight was selected based on analytical analysis. That is, uh, if we keep into account the buoyancy of the cubic container in which the payload weight would adjust, and then look into the maximum or the complete vertical thrust force applied by the vertical thrusters. Uh, these two will be applied in one direction because the buoyancy is applied upward, and the vertical thrust, if they apply upward, they would have a total upward force. So adding them together uh, will give us the value for the payload, which should apply to keep the system at position. So that is the maximum payload at which the 12775 Newton is the maximum payload at which the system would be kept at a position. And this will provide the payload mass of 13202 kilogram. So some initial verification tests were performed to get confidence on the system that this simulation model for this system is giving the right results. So in the first test, the payload mass was kept to the maximum, and all the vertical thrusters were applied at the maximum values. So analytically, it was worked out that the system should not move because the weight and the buoyancy are balanced. The weight and the buoyancy plus the vertical thrust forces are balanced. But in the dynamic model, because here we looked into the dynamics, there is a small spike in the vertical motion, but eventually it ends up at near zero. So it's verified. In test two, the conditions were kept as in test one. That is, the payload mass was kept at the maximum, and all the vertical thrusters were applied. All the axial thrusters were applied inward. That is, the when all the AUVs they apply their axial thrusters positively, they are applied inwards. So as can be seen in the test two result, that the small spike in heave is still there, but there is no motion in the axial direction. So which is good. That it means that the dynamic model is giving the right results. So after the initial verification test and getting confidence in the model, I looked into the sea current effect. So first, a study was done that how much sea current velocity or sea current force uh, can the system bear. So it was looked that the velocity of sea current depends on sea depth and the area of operation. In some of the areas, such as the Strait of Gibraltar, the sea current can go up to 30 meters per second. But generally, they are measured between 0.01 meter per second and 0.2 meter per second. So keeping the maximum of this range, the payload limitation was kept at 0.2 meter per the sea current was kept at 0.2 meter per second, and then the payload limitations was set accordingly. Then some tests were performed with including the sea currents. As can be seen in test 4, that when the sea current velocity was applied at 0.2 meter per second opposite to the upward motion, and keeping the maximum payload mass of 13202 kilogram, all the vertical thrusters and applying all the vertical thrusters at their maximum, the vertical position is not kept due to the sea current effect, obviously. So then analytically, it was worked out at how much force or opposing force was applied by the sea current, and it was worked out to be 200 newtons. So same force was when converted into the mass, and taking that mass out of the total payload mass, it came out to be 1269 kilogram. So now keeping that mass and applying all the vertical thrusters at the maximum, test 6 was performed, and it can be seen that with a small spike, the vertical position is kept. So payload mass was then limited to 1269 kilogram, but it is also said that the safe operating payload mass is 1200 kilogram. Control system was designed. As I said, centralized control system is enough for the rigid connections between the vehicles and the payload. So the control system was designed using the PID controllers, which were applied on the difference between the desired and actual states, and the outcome was given to the thrust vector, which was then multiplied with the inverse of the transformation matrix to get the desired thrust vector in the body fixed frame. That thrust force was then multiplied with the inverse of the thrust allocation matrix to get the desired thrust force vector, and then the saturation limit of the forces were applied to get the actual thrust force, and that actual thrust force was then again given to the system propulsion model to get the actual thrust vector, which was given as control input to the system dynamic model to get the actual state vector. And then that state vector is again compared to the desired state vector, and the process continues until we get the zero error. But then the motion response was looked into with the control implementation. So in test 8, the desired axial distance was kept 10 meters, and the C current was applied at 0.2 meter per second. And it was desired that no motion should be there in other directions. Keeping the PID gains as shown in the table, though the propulsion gain is a little higher, and which is obvious because it has to overcome the C current velocity, which is applied right opposite to the axial direction. The desired axial distance is obtained in around 35 seconds. And the good thing is that there are no motions in the other direction. From the thrust force analysis, it can be seen that the combined damping force, which was the combination of the drag forces and the resistive forces due to the C current, the maximum damping force was observed minus 1600 Newton. So to overcome this, the thrust force was applied at 2000 Newton, at a maximum of 2000 Newton, to overcome the damping forces, the resistive forces, as well as move the system towards the desired location. And obviously it was then reducing over time.
You have about 5 minutes, please.
Okay.
Fahim, you have about 5 minutes, please.
Okay. So then they were reducing as the system approaching the desired location. In test 9, the same requirement as in test 8 was set for the C current, that is 0.2 meter per second, but now it is applied in the vertically upward direction. Keeping the same PID gains, as can be seen in the test 9 displacement response, that though there is PID control applied in the vertical direction, though it is low in value, the vertical position is not kept by the system, and it is moving upward and covering a distance of around -5 meters in 50 seconds, whereas the axial distance is covered but with oscillations. Moreover, there are pitch oscillations observed, which are continued even at the end when the displacement is somehow reached. So the PID gains were then modified, keep increasing the PID gains of surge, heave, and pitch. But even then, from the rotation response in test 8, it can be seen that there are fluctuations around zero position in pitch, and there's some offset in the X position after reaching it, and though the Z is kept at zero after some time, but there are still oscillations. So in conclusion, I would say that uh, the system was developed and verified, uh, and the payload limits were set accordingly. The control system was designed with the PID controller, which was successful in overcoming the C current when applied right opposite to the direction of motion. But when the C current were applied perpendicular to the direction of motion, higher PID gains were used. Even then, there were some pitch oscillations and small offset in the motion response. And because of the high PID gains, the system would be sensitive to noise, which is not good. So it is recommended for the future that optimal controllers be explored, and C current effects should look at higher rates in future. That would help to analyze the C current effect in more detail. Yeah. So these are some of the references. And by this, I thank you all.